Okay, I think I'll start. We check video. It's not off. Sound is off. Okay. If you cannot hear me, please let me know. Okay. Send me a message. I'll look at the chat. I think everybody is hearing me. There's no problem, I hope.
Yes, hocam.
Okay. Today I will be discussing two positions of a rigid body. What I mean by that is, I think you can see the screen, Google Geogebra screen. I have a rigid body. This rigid body can be of any shape.
Hocam, we see the PowerPoint slides.
Okay.
Not GeoGebra.
Okay. In that case, what I will do is this. I think okay. I have to do it like that. Here is a rigid body. I have it, shape. I can change this shape to any other thing you think, because what I mean by a rigid body is it can be a part of a machine. It can be the cover of something. It can be any kind of a rigid body that you may have. Okay, it can be a part of a furniture, the door of a furniture, or it can be a part of a car, anything. And it can have any kind of a shape. I want to move this rigid body from one position at time t is equal to 0. This rigid body is over here. And at time t is equal to t1, this rigid body is over here. Now, the first thing I have to do is, I have to, in order to formulate this problem, I must select 2 points. Because a rigid body can either be described, the position of that rigid body in plane can either be described by a coordinate system. I can attach a coordinate system and give the origin of the coordinate relative to the fixed frame, and then give the angular rotation of that coordinate system relative to the positive x-axis of the fixed frame. That I can do. Or I can select any 2 points on this rigid body and give you the location of that rigid body. For example, I can select this point. Sorry, not that one. Let me move it like this. I can select this point and this point. But if you want, I can select this point and this point. So depending on the observer, depending who is doing this, solving this problem, you can represent the motion of this rigid body by these 2 points. Okay? Any 2 points. So it depends on who's performing the analysis or performing the motion, or who's observing the motion. What I will do is, I will select 2 points, A and B. Oh, sorry. B. I will select these 2 points. At time t is equal to 0, AB is over here. Notice. At time t is equal to t1, AB is over here. Now, let me repeat. A and B are 2 points on that rigid body. It doesn't matter which 2 points they are. But I have to select 2 points to represent this motion. Now, in order to perform my analysis, you see, what I do is I go over here, somewhere over here. I mark these 2 points, A1, B1. Those are ABs in the first position. In the second position, AB is over here. Then I mark AB and use subscript 2 to mean that it is at time t is equal to t1. It's in the second position. And call it A2, B2. Now, the thing is, A1, A2 refer to the same point, AB, on this rigid body. It is the position of AB in the first at time is equal to 0. It is the position of AB, A2, B2 is the position of AB at time t is equal to t1. Okay? So these 2 positions do not exist at the same time. However, what I have done is I have projected these points. I have marked these 2 points at time t is equal to t1. I marked these on a fixed frame, A2, B2. And then at time t is equal to 0, I mark these points on the same sheet at the back, and that is A1, B1. Correct? These are the 2 points. Now, the problem is, you see, normally in real life, what you see is you don't see points A, B. You see a rigid body moving. And you are asked to, okay, this is my body, move this body from this position to this position. That's all they say. Now, these are the things that we have to perform so that we can analyze, we can perform our calculations. A1, B1, A2 are the same 2 points AB on that rigid body. It is the projection of those points to the fixed frame, to the fixed plane. We call A1, A2, B1 homologous points. Homologous means it is the same point A on the moving body. It is the position of A at different locations, at different time intervals. A1, A2, B1, B2 are pairs of homologous points. Okay, that is the definition. Now there's a guy with the name of, I stop sharing, I'll share again, this time. This one. There's a guy whose name is Michel Schall. I used to call it Chasles, but French, but one of my friends who knew French said it is Schall, not Chasles. It is Michel Schall. In 1860, came up with a theory. Actually, it was in 1760, 1730. No, 1830 is what Charles said. It was in 1760. Another guy, Mosey, was the first to say this theorem, which is, they say the translation of a rigid body in plane motion occurs most simply by a rotation about the pole P12, which is located at the point of intersection of two of the perpendicular bisectors of 2 pairs of homologous points. Now, let me repeat, homologous points are different locations of a point on the moving frame at different positions of the frame, projected to the fixed frame. Okay, that's the definition. Now, how do I do that? Okay. Let me go back to Geogebra. I will forget the subject. Now I can, you see, I have represented my 2 positions with AB. I can forget about that rigid body. I have these 2 positions, 2 positions. I have two pairs of homologous points. A1, A2 is one, B1, B2 is the other. What Charles says is you can perform this motion from this first position to the second position most simply by a pure rotation. And he tells you where to rotate that rigid body. He says, take the perpendicular bisector to the homologous points, A1, A2. This is one perpendicular bisector. This perpendicular bisector, I will name it as A-1-2. It is the perpendicular bisector to A1, A2. And then draw another perpendicular bisector to B1, B2. Okay, this perpendicular bisector I will call B-1-2. That is B12. Okay. Now it is the intersection of these two perpendicular bisectors. This point. This point is what we shall call P12, P-1-2. That is pole, rotation pole, usually it is called pole or rotation pole. Now, he says that you can rotate this rigid body to move from the first position to the second. Meaning, if I form a triangle, rigidly connect that AB, that rigid body, that plane, by attaching a revolute joint at P12, I can rotate this rigid body from the first position to the second. You know, originally, we don't know the shape of the rigid body. We are going to assume that rigid body, the moving plane, is of infinite dimensions. Now, what we mean is determine that point P12, attach that plane to the fixed frame by a revolute joint over there. Now, this is his theorem. You are able to rotate this rigid body from the first position to the second by a pure rotation about P12. Now, can I prove this? In order to prove it, I have to prove that the triangle we see, P12, A1, B1, is equal to, exactly equal to, P12, A2, B2, not similar, equal. In order to do that, I have to prove, as you can see from the figure, side P1 to A1 must be equal to side P1 to A2. Side P1 to B1 must be equal to P1 to B2. A1, B1 is equal to A2, B2. Why? Because it is a rigid body. I have selected this rigid body. It corresponds to AB on that rigid body. So AB, A1, B1 has to be equal to A2, B2. Now, the problem is P1 to A1 equal to P1 to A2? The answer is yes. Can somebody tell me why? Because the property of perpendicular bisecting. When you have, let me select 2 points. If I have these 2 points, if I draw the perpendicular bisector to these 2 points, any point that I select, any point that I select on the perpendicular bisector, FH will be equal to HG. The reason? Look. perpendicular bisector bisects this angle. So if this point, let me call this, I don't know what the Geogebra will call that intersection point, Fi will be equal to Aig. This is perpendicular, this is perpendicular. So FH, IH is common. So the hypotenuse of these two triangles has to be equal. Nowhere, let me show KL. As you can see, they are equal. Now, wherever I move, sorry. As you can see, every point on that perpendicular bisector will be equidistant to these 2 points which it bisects. Okay? So that means A1 P12 has to be equal to A2 P12. Actually, any point on A12, this perpendicular bisector, will satisfy this condition. B1 P12 is equal to B2 P12, P12 B2. Again, with the same reason, because it is the perpendicular on the perpendicular bisector of B1 B2. P12 is also on B12. So that means those this is side B1 is equal to B2, A1, A2 is equal to A3. Meaning A1 P12 is equal to A2 P12, B1 P12 is equal to B2 P12, A1 B1 is equal to A2 B2. That means these two triangles are exactly the same, which means this rotation with P12 fixed, these two triangles are exactly equal. The motion occurs without any deformation of the plane, of the moving plane. Now let us look at the angles. A1, these two triangles are equal because side, side, side. They are equal, the three sides are equal. Now, let us look at certain things. A1, P12, B1, this angle, I'll call it alpha, is equal to A2, P12, B2, which is equal to alpha. Reason, these two triangles are the same. Now consider the angle A1, P12, A2, this angle. Let me describe that angle. I will rename it. It's called alpha. Alt F -1 -2. I don't know. Okay. I cannot. No. Okay. That's phi12. For this case, it's 48 degrees. I don't care. The angular rotation, you know, it's not important because it can be any two positions. So forget about it. Now let us look. A1, P12, B2 is equal to A1, P12, A2 plus A2, P12, B2, which is from A1, P12, B2 is equal to alpha plus phi12. This angle is phi12, this angle is alpha. So it is alpha plus phi12. Can everyone see that? Now let me do it another way. A1, P12, B2 is equal to A1, P12, B1 plus B1, P12, B2. Now what can you say? about the angle B1, P12, B2? Can somebody tell me, please?
Same as phi 1, 2.
Yes. Every point, the line joining that point, any point, to the origin is rotated by an angle phi 1, 2. Okay? Phi 1, 2 is independent of the point A1, B1 that I have selected. Okay? Phi 1, 2, this angle is the same for any point, the line joining any point on, to P12 rotates by an angle phi 1, 2. Whereas this angle alpha will depend on the point. For example, let me consider another point on this moving frame. The way I will do it is I will select one point on this rigid body. I will have problem with it later, but okay, let me think of like this. In order to determine the second position of J, this point I will call C-1. It is the location of a point C in the first position. It's a point on the moving body in the first position. Its location is at C1. To determine C2, I can do it this way. I can draw a circle from A2 of radius M, because that is this A1, C1 distance is M. Since it is a rigid body, it has to be equal to M. And then from B2, draw a circle with radius N. As you can see, these two over here. Now, the point of intersection is going to be this point. I'll call this point C-2. Okay. Now, if I draw the perpendicular bisector to C1, C2, this I will call C-1-2, small c, small a. Again, the perpendicular bisector to C1, C2 passes through P12. Any point, if I select any other point, the perpendicular bisector of that homologous point, every homologous point, the perpendicular bisector to every homologous point will pass through P12. Is that agreed? For example, here is C1, C2. Is that agreed? That's C1. I have another point C1 like that. Its perpendicular passes through. Oh, my triangle is on the other side. It's turned over. Now let me consider
John,
one. Yes, sir.
may I ask you a question?
Of course.
Can we select the points not in the object, but out of the object in space?
You see, right now, I'm assuming my plane, my moving plane, is of infinite dimensions. Okay? So you cannot select any point outside infinite dimensions. Is that agreed? Every point that I select over here, even if I select over here, move this C1 over here, that is a point on the moving body. For the, you see, the physical shape of the rigid body that I am going to move at this instant is not important. It is important when you are applying this theorem. At this instant, I'm assuming a rigid body, a moving body, which is of infinite dimensions. Is that agreed?
Yes,
so
hocam.
any point that I select, either here, whatever, wherever you like, I can select this point. Is that agreed? That's the point on the moving body. That's a point C on the moving body at two positions. Is that agreed? That's the beginning.
Yes, hocam.
And one other thing is, you see, when I have the one triangle, those two triangles are not the same. If I have, take the image of this triangle along AB, it corresponds to another point. That's when in Geogebra, if I do it like this, notice these two triangles are not the same. C1, C2 is not the same point C on the moving body if you do it like this. Can anyone see that? This is wrong. One other thing is, if I join this point C, I'm trying to find a nice place to do that. Okay, I'll do it like this. If I join C1 to P1 to P12, join C2 to P12, and that angle, C1, P1 to C2, that angle will also be equal to, yes, phi 1, 2. Okay? That angle is also equal to phi 1, 2. Any questions? Let me prove that. Very simple. If you consider the angle A1, P1 to C1 is equal to, let us call beta, is it also equal to A2, P1 to C2? That is beta because it's a rigid body rotating about P12. If A1, P12 be A1, A2 is equal to phi 1, 2, you add and subtract beta, so C1, P1 to C2 is equal to phi 1, 2. Okay? The same reason that I have stated when I showed A1, P1 to A2 is equal to B1, P1 to B2. Is that it? Okay. Now I will delete this line, enlarge this a little, hide these points because it's making it complicated. Hide the labels. Okay. Okay. Now, this is the problem. I select, let us show that it's the rotation. Over here, angle. I'll call that angle alt phi. It's going to change from 0 to 48 degrees. Okay, like this. What I do is translate, sorry, in this case, rotate only. Rotate this rigid body about P12 by an angle alt phi in counterclockwise direction. This is the final thing. That point I'll call A. Don't worry, the other A will change. This point I'll call B. That is my rigid body moving. Okay? Now, we have invented the wheel. This is the wheel. This is the simplest mechanism that you can design to move a rigid body from one position to another. And believe me, almost 50–60% of the motion problems are solved in real life, are solved using two-point synthesis, using the pole. Almost 50%, more than 50% of the problems are solved because this is very simple. This is why we have doors rotated to open and close. This is why we have the, lots of things are done by rotation. It is the simplest mechanism that you can design. If you can move a rigid body from one position to another by a pure rotation, please, please do not look for any other solution. That is the simplest, that is the easiest, that is the best way of obtaining a motion, okay? This is invention of the wheel. That's why the humankind first determined this, rotate. But we have a problem. You cannot always do so. There are lots of reasons why you cannot design, move a rigid body by a pure rotation. Number one, there are cases where P12 is very far away, okay? When P12 is very far away, the rigid body that you have to construct will be too big. At this instant, I have, even if it is too far away, you can do that. But the thing is, if it is too far away, this rigid body has to be too large. Am I correct? If you are going to move, let us say, a box, and P12 turns out to be, a box of 20 by 20 centimeter length, height, depth, etc. Something that you can hold in your hand. And then the pole, P12, is 2–3 meters away. You have to connect that box to that P12. That is not reasonable. That is something that, I will again share. This is what I explained initially. I have shown this, okay. Here is the case. When the pole is too far away from the rigid body. Another thing is, consider this case. You have a gate, which is inside two walls, like this, and then it has to be opened like this. Here is the point P12. Can you rotate this rigid body? The answer is no, because the obstacles will not permit you to rotate that rigid body about P12. You have to first move this rigid body forward outside the obstacles and then rotate. Can everybody see that? So depending on the obstacle, depending on where P12 is, you cannot use this pure rotation. Let me repeat, pure rotation is the simplest mechanism that you can design. No problem. You don't design mechanisms for the sake of mechanisms. You design mechanisms to perform a certain task which cannot be done otherwise. Is that agreed? You have there must be a reason for designing a mechanism. That's very important because you don't design it for this, it is not fun. It is not, just for fun. It has to do, we engineers solve problems of the mankind. We engineers solve real down-to-earth problems. We are not physicists or we are not chemists, we are not scientists. Scientists can think their own problem and solve. We engineers solve what is required. We engineers solve what exists, what is an existing problem. And because of that, you don't solve for the sake of mechanisms. You solve if there's a need. Let me repeat. If you have a motion requirement, the simplest mechanism you can design is, let me repeat, pure rotation. If you can perform your motion requirement by a pure rotation, please don't look for anything else. If not, now I have to search for a new solution. Okay, I will again switch to, I don't know how to switch from here in here. Oh, now new share. Okay. I got it. Let me erase this triangle. Let me erase this as well. I am deleting, I'm not going to use it. I will delete this one as well. I have the pole, I have determined the pole and rotation about the pole. These are my perpendicular bisectors. Now what I can do is, if I cannot rotate about P12, this rigid body, what I can do is, I will pick up a point on A12, insert a revolute joint to the fixed link, rename it as A-0. And then I will pick up another point on B12. Let me say this point. And rename this point as B-0. Any questions on this? Now, I will attach a link from this revolute joint, moving revolute joint, to this fixed revolute joint, one crank. I will forget about the label. I will attach a link between B1 and B0. Now I have a 4-bar mechanism. Now my claim is, I have to prove it, that A0, this 4-bar mechanism, A0, A, B, B0, will exist in the second position as well. Meaning, this 4-bar will also exist. Let me change the color of these links. For the second position, I made it red. Now my claim is A0, A1, A0, A1, B1, B0 will also exist, that 4-bar will also exist at A0, A2, B2, B0. Let us prove that. A1, B1 is equal to A2, B2. Why? It is a rigid body that we are discussing. Okay, AB, A1, B1, A2, B2 corresponds to the same point AB on that rigid body. So it is the same. A0, A1 is equal to A0, A2. Why? Because A0 has been selected on the perpendicular bisector A1, 2. Any point on perpendicular bisector is equidistant to A1 and A2. Any questions? Similarly, B0 is on the perpendicular bisector B1, 2. So any point on B1, 2 will be equidistant to B1, B2. So that means A0, A1 is equal to A0, A2. B0, B1 is equal to B0, B2. A1, B1 is equal to A2, B2. A0, B0 is the same. This 4-bar will exist at these two positions. Any questions? This is very important. I don't have a unique solution. And in fact, I can select AB anywhere I like. I can select AB anywhere I like on that rigid body. I will have different solutions. I will show it in a minute. There are lots of solutions. Now, again, let me show something. This time I'll call this angle theta. Angle theta. 0 to 360, I don't care, I do it like this. Once I have the 4-bar, now I'm going to perform the analysis to show you that it is possible. First, I will draw a circular arc with center B0.
Hocam, may I ask a question again?
Of course.
So, assuming that if we have a perpendicular, additional perpendicular bisector, and then we have 3 points, can we do that for more than 2 points? If you have more than 2
that
perpendicular
bisectors. A ME301 question. Can you have a mechanism as such?
I don't know. I tried to imagine that if we have a point C1 and we have an additional bisector, it did seem it might occur, but I'm not sure. I cannot imagine it very clearly.
If you have, let me draw it like this. Okay, I will simply freehand. I have these 3 points, the same rigid body, correct? Like this. If I have 3 points fixed, like this is fixed, this is moving. I don't care about the lengths, etc. If I have links attached, if I have a mechanism like this, what is the number of links? One of the GHI is fixed, let us say. Number of links is 1, 2, 3, 4, 5. Number of links is 5. Number of joints is 1, 2, 3, 4, 5, 6. F is equal to 0. It is immovable unless it is these loops are parallelogram. Is that agreed? So that means you cannot have more than 2. Can everyone see that?
Okay, hocam. Thanks.
Is that okay? So selecting 2 points is enough. It will be constrained 1 degree of freedom mechanism. If you select 3, sorry. Okay, you can select any 2 points. You know, you can select B, fine, BF, fine, AF, fine, but not all 3. Is that okay? Just for the hell of it. Is that agreed? Is that clear? Okay, I'll delete these and then continue. Okay, this is the path. Whenever you select B0, B1, this is the path of B1, B point B. You see, originally, this path is not given. 2 positions are given. Whenever you select B0, this path is defined. Is that agreed? Now, this length, show label F, okay, to determine the length. What I will do is this. First, I will rotate A1, A0 about A0 by the angle theta. I think you can see it, it's over here. Then I will draw a circle with center A, radius S, that's the radius AB. I will determine the intersection point, not this one, because as you can see, B1 is forward on the right. This is my 4-bar mechanism in motion. Let me do it like this. Sorry. Increase the thickness. Make this blue. Increase the thickness. And make it green. Increase the thickness. These points, I will keep it black, but increase the size. Okay, that will do. Now I will be able to move my rigid body, as you can see. This is right over here. It is, after that, it is locked, I guess. Is that okay? Is it unique? The answer is no. Here I have another 4-bar proportion. I don't know whether this will move or not. Yes. Let me do it like this. You see, I can select it anywhere I like. Oh, it has to rotate. I have to change it. Again, object properties. I don't know where, oh, no, the slide I have to say. It has to be, I have to select counterclockwise, but I cannot find that. Maybe it's below. No. I have to select counterclockwise. Basic. It should be somewhere here, but I couldn't find it. It has to rotate, in this case, it has to rotate counterclockwise. Let me do it like this, to rotate it counterclockwise. Oh, no. You see, I have plenty of solutions. However, some of which is not possible because the motion in between these positions will not exist. Okay? There are infinitely many solutions, but some of the solutions will not be something that you can apply. You cannot use that solution. Okay? Any questions on this? Okay. Let us look at the number of parameters we have. Let us look at the number of parameters. I can select A, B in infinitely many ways. Can I see that? A, B is any 2 point on the moving body. Let me go back to okay. I can select A, B anywhere on the moving body. To select A on the moving body, I have to specify the X and Y coordinates on that rigid body. So that means selection of that point A requires 2 parameters. I can select X infinitely many ways, Y infinitely many ways for A. And similarly for B, I can select infinitely many ways, both its X and Y coordinates. So that means selection of A and B requires 4 parameters. There are 4 free parameters that I can use. Correct? Coordinates. Once I select A, you see the perpendicular bisector is going to be unique. Whenever I select A1, A2 is unique, and this perpendicular bisector is unique. Correct? So that means I can select A0 anywhere on this perpendicular bisector. So I have 1 additional parameter. For the selection of any point A, I have 3 parameters. And if I'm going to use that as a revolute joint, okay, then its center will be over here, A0, and that will require an additional parameter. So that means 3 parameters for the crank A0, and 3 parameters for the crank BB0, For the 4-bar, to move a rigid body from the first position to the second, using a 4-bar mechanism, I have 6 free parameters. Coordinates of A, coordinates of B, coordinates of is 4. The center, the distance, the selection of point A0 or and B0 on the perpendicular bisector requires another parameter. So I have 6 free parameters. Now let us look at one parameter, this selection of A0 on the perpendicular bisector. I can determine this point, the midpoint of A1, A2, and then determine the distance, select the distance from that midpoint to A0, one possible parameter. Or I can select the distance from P1 to A0, another parameter instead of that parameter. One other parameter that I can select instead of the distance from P1 to A0 is I can select the crank length, A1, A0. Once I select this crank length, I draw a circle. Intersection of that circle with this perpendicular bisector will give me A0. So I can select AB anywhere. I can use polar or rectangular coordinates, doesn't matter. And then I will select the crank length A1, A0. Okay, now I'll go back. New shape. Now I will again erase this 4-bar. I'll simply keep the first, the 2 positions. Okay, I think if I erase this, those will be erased. Okay, that's good. Delete. I will, in fact, I will delete this as well. I will delete. Okay, I will not delete that, but I will do like this. Delete. Delete. Okay. Now, I'm not going to select AB as my revolute joints. You see, AB I have used to describe the motion. Since as I said, I can select A1, B, the revolute joints anywhere on the moving body. I will select a point C on the series body. I will call this C-1. You see, the names I give, okay, the names are what I use. I can use any name you like. And I will select another point. Like this. Oh, sorry. I will delete this. If this is A1, B1, what I will do is, since I can select my revolute joint using 2 parameters, I will determine that revolute joint with respect to this line AB. So what I will do is I will have 2 parameters. One is the number. I will call it R-A for A. It will not be 0. Well, I could have made it 0, 10, or no, 13, let me say. these lengths you can change. This is RA. And I will select another parameter. These are parameters. Angle parameter, alpha dash A, you can call something else if you like, from 0 to 360, like this. Okay. If this is A1, B1, I don't know whether it's horizontal or not. What I will do is I will measure an angle out alpha dash A from that line A1, B1. It rotates it like that. This is the line, making an angle alpha A. And then I will draw a circle, R dash A. Oh, sorry, it has to be small. Correct? Oh, sorry. This point I'll call C-1. You see, I can, let me hide this. This is a point on AB, on the moving body. I can change its location using these two slides, two parameters. Using these two parameters, I can change the location of C1. Is that okay? Now, I will do the same thing. First, let me do something else. I'll hide this as well to simplify my shape. I will do the same thing to determine C2. Since this is a rigid body, the distance AC is not going to change. This angle is not going to change. So what I will do is repeat what I have done for the second position. Alt alpha dash A, correct? And then, sorry, first I have to draw this line, this ray, hide this, draw the circle, because that distance is not going to change. R dash A. C-2. Okay. Oh, no. It has to be capital. That's C2. I can hide the angle as well. I don't want to. I'm hiding it. I'm not erasing them. I will repeat the same thing for another point D. Okay. I called it okay, R dash D from 0 to 40. I don't care. I mean, usually you have a certain value. Later, you may have to change it like that. And okay, and then I will have another slide. Angle alt alpha dash D. Okay. Repeat the same thing from A1. Measure. Can I use, sorry, can I use B1 for this as a reference? Yes. It doesn't make any difference. Alt alpha dash D. Again, draw your ray. Hide this. Hide the object. Draw a circle with radius R dash D. Okay, no problem. Hold this point. D dash 1. Let me take it like this. Now I have the same rigid body like this. Correct? Let us do the same thing for the point D, position 2. Alt alpha dash D. Correct? Draw your ray. Draw your circle. R dash D. That is your point D at position 2. Now, let me see. C2 is over there, so I will do it like this. So that the two do not intersect. This is my rigid body. I'm going to attach revolute joints to C and D. C and D I will call moving pivots. I can call moving pivots because those are the revolute joints which will be rotating, moving. Or I can call it circle points because once I attach a crank to it, they will be on a circle. C1, C2, C1 will be on a circle. C and D, I can either call it moving pivot, I'll call it circle point, and the corresponding center, I will call fixed pivot or fixed pivot or center point, because it is the center of the circle described by C or described by D. Again, I will repeat my process. You see, we're using these 4 parameters. Now these are my parameters, you see. I can change my parameters and obtain different locations for C and D, for the moving pairs. I can do it like this. Once I select C1, D1, C2, D2 is automatically determined. Notice? Or vice versa, because these are the 4 parameters that I will use. I have used polar coordinates in this case. I could have said, okay, distance X from A1, distance Y from B1, relative to B1, A1, but that will be more complex. These are the 4 parameters. Now, all I have to do is select the perpendicular bisectors for the moving pivots that I want to, okay? If CD, if I'm going to attach revolute joints to C and D, I will use this perpendicular bisector for C1, C2, rename it as C-1-2, and I will use this perpendicular. Again, it will pass through P12 that I have found. Remember, we said that. This I will call D-1-2. Now, as I said, I will, in order to select C0 and D0, they will be on this perpendicular bisectors. I have one additional parameter. I will use the link length CC0 and the link length DD0 as my parameter. So what I will do is attach 2 new parameters. Number, I will write it like this, C-0C. I don't know whether this is the first time I'm doing it, so please bear with me. 20 to 120. I can change these if I don't have the intersection because there will be. If I have it small or too large, it's okay. And then, yes, that's correct. This will be more meaningful if I give it the name C0C. And then I will have D-0D. I think okay. Again, from 30 to 150, okay. Now I will draw a circle with center C1 of radius C-0C. Oh, see, I have it too big. Changed object properties, basic. Oh. Oh. I'm sorry. I shouldn't. I know I was able to change the limits, but now I can't see it. Let me see. Okay, I'll delete them. Oh. Okay, I'll start from 0. Sorry. I will start from 0 to 100. Okay, and then I will have d dash 0d 0 100. Okay, I will draw a circle. C dash, sorry, 0C from C1. This is what I was saying, okay? If it's too small, there will be no intersection of this circle with this perpendicular bisector. You cannot do it. So I have to increase the size. Correct? You can also select it if you want your fixed pivots below, you can select this point as well. But that is, I will select the top one, rename, C dash 0. I think I can hide this. And then center this D1, D dash 0D, increase it. Then I select this point, rename it as D dash 0. Now I have a 4-bar mechanism. 0, 0, C1, D0, D1, first position, C0, C2, D0, D2 in the second position. Now, using these 6 parameters, notice, I can change the dimensions, I can select, I can determine different solutions to move this rigid body from the first position to the second. For example, I can increase the crank length, C0C. I can increase D0D. Correct? I can change the location of point D. I can move it this way. Okay? Now, as I have done before, these are the design parameters. I have 6 design parameters, notice. You are able to select 6 of these. So the number of possible solutions we have is what we call infinity to the 6th. Infinity is too big. Infinity to the 6th power is very, very big. Okay? You have a huge number of solutions, as you can see. You can change these 6 parameters. Usually, whenever you have so many parameters, it is possible to find a good solution from those, but it is much harder because if you are going to do search, you have an infinite possibility. So it's really hard to search. However, not all these solutions are possible solutions. Okay, these are theoretically possible. The reason is we have nothing to say about the motion in between. We have a 4-bar, yes, but we don't know anything about the motion in between these two positions. We know the 4-bar is going to exist at these two positions. Okay, the 4-bar is going to exist at these two positions. In order to not to confuse, what I will do is I will make these lines dashed so that you know it's the second position. And change the, okay, I'll change the color as well. Let me see. Okay, now. At least you can see it's the second position, first position, second position. Okay. Now, okay, I want to animate it. Fine. Usually, you have to hide the labels, etc. But you know, it takes time. Okay. Okay. At least I have created some of the labels on the board. Now I can animate it. Let me repeat. Now I have another parameter, but this is not design parameter. This is the motion parameter. Alt T, theta. Okay. Oh. First of all, I will rotate C1, D0. You can rotate D1, D0, by the way. You can take it as a crank, or D1, D0 can be cranked, depending on the problem. Okay. Let me. This is going to be my point C. I have to get the label. I think it is Q1. I can see that. I don't know. I'm not sure. Girebilirsin. Tamam. Sağ olun. Teşekkür ederim. D0 center from D1 to D2, like this. I'm not sure, but I'll try that. This is Q1, C1, D1 neck is Q1. I'm not sure. I can do, I think this is the label. From the label, I can see that. Draw a circle with next Q1. It's not on, no, that's not. Oh. Sorry. Yes, C1. I'm sorry. Okay. C-1 is the length of C1, CD. Okay. This is the point of intersection. This point I'll call D. Okay. So my 4-bar, that will be moving. Is that 4-bar? Notice I can move it like this. If you want to see A1, B1, it is, let me show that as well. It will take some time. Okay, let me hide these. Okay. The first thing I have to do is determine the angle between CD and C1D1 so that I know how much this has rotated. So what I will do is determine the angle between this line and this line. This is psi, 335.41 degrees. Rename that psi. I don't know how to write it, so I will rename it as gamma. Now this is what I'm going to do. Please follow me. Okay. Okay. First, I will translate this body, moving body, from C1 to C. That's translation. And then next, I will rotate this rigid body about C1. Sorry, first I have to select the rigid body. Rotate this rigid body about C1 by an angle out gamma. No. The gamma angle, yes, it didn't rotate by the angle gamma. Oh, minus gamma. Let me try that. Yes. Next, I will hide this intermediate position. Hide it. hide that angle. I don't need it. I can rename these, but I don't think I spend too much time. Okay. Let me hide this as well. Oh, no. I cannot. Okay. In those cases, what you do is you hide it like this. Okay. You have to rename these, but okay. Now you see what we have done is we have constructed our forward to move our rigid body from the first position to the second. And we have infinitely many parameters with which we can change and find different solutions. Okay? We can find different solutions for our problem. This is another solution. Now, depending on the application, depending on the practical problem, one solution will be better than the other. You have to check the transmission angle. You have to make sure that your mechanism moves in between the positions, correct? You must check the transmission angle, for example, because if you are going to transmit large forces, it will be a problem. You have to check whether there's an interference with other parts of the machine. Okay, it's possible that this thing is not going to operate all by its own. There will be other things around, so you have to check that. There are lots of things that you have to consider before your selection. However, as you can see, I have 6 design parameters. I can very easily analyze. I have to analyze the mechanism. I can change these design parameters and see whether I have a good solution or not. And with this, I can design a 4-bar mechanism which will realize this motion. Is 4-bar the only solution? Hell no. Number one, okay, I think I have covered these. You must always check your resulting mechanism. Okay, there's no guarantee in between the positions, the motion in between the positions. If I select my slider axis along a B1, B2, if I select my or fixed pivot at infinity, if I select that point, okay, I'll again switch to Geogebra. If I select D0 at infinity, what will happen? D1, D2 will be on a straight line. As you increase D0, D1, as you can see, this line is going to be a straight line. In that case, what you can do is instead of having a link of infinite dimensions, which is 100, and D1, D2 is almost a straight line, as you can see. There's no rotation. There's no, it is almost a straight line. If D0 is selected at infinity, D1, D2, I can attach a slider to it, okay? I can obtain a slider crank mechanism. C0, C1 is the driving link, crank. I will have a sliding joint at D1. I can attach sliding joint at C1 and could use D1, D0 as a crank. That's also possible. Okay, but in this case, since I have selected, okay. Let me move this to infinity. Let me see what happens. It will be almost a straight line in that case. Okay. C1, C2 will be a straight line in that case. I can have another type of slider crank mechanism. You know, select one of the points as D0 at infinity. If I select both of them at infinity, I will end up with what we call double slide. You can have slider crank or double slide. Again, let me repeat, you must check your motion. There is no guarantee for the motion in between the two positions. And there is no guarantee, you see, the transmission angle can be terrible. You will not, for example, a case like this, where this coupler link is almost perpendicular to the slider axis, you will not be able to move the rigid body in those cases. Let me derive certain relations in case of a 4-bar, any 4-bar that we design. Now, the thing is, A1, P1 to B1 will make an angle alpha. That angle will be equal to A2, P1 to B2, because it's a rigid body motion. That angle alpha will depend on A1, B1 that you have selected. A1, B1, you can select in infinity many ways, so alpha may change. However, the angle A1, P1 to A2, which we call phi 1, 2, is true for any point A that you select, as long as the position of the given two positions are the same. For B1, P1 to B2 is equal to phi 1, 2. If I select a point C1, P1 to C2, it will be equal to phi 1, 2. So the motion, we say, when you are given two positions of a moving plane, P12, this point P12, and the angular rotation phi12 is invariant. It doesn't change. Whereas depending on the points that you select, A, B that you select, alpha will change, and the shape that you see will change. But what is important is phi12 and P12 is invariant. It doesn't change. Now, another thing. If you consider, okay, that's what I have proved. Consider A1, P12, B2. This angle, this total angle, is equal to A1, P12, N. N is on A12, perpendicular bisector A12, plus N, P12, M, perpendicular bisector B12. It is the angle in between the perpendicular bisectors M. And M P12 B2. M P12 B2. A1 P12 N, because of the property of the perpendicular bisector bisects the angle A1 P12 A2. So if A1 P12 A2 is equal to phi 12, A1 P12 N is going to be equal to 1/2 phi 12. The perpendicular bisector B1 P12 B2 is phi 12. M P12 B2, since M is on the perpendicular bisector, is again phi 12/2. Now, the total angle A1 P12 B2 is equal to phi 12 plus alpha. Correct? Phi 12 plus alpha. From, if you select A1 P12 B1, alpha, plus B1 P12 B2, phi 12, alpha plus phi 12. Now, this angle is phi 12/2. This angle is phi 12/2. The angle between N P12 M is equal to alpha. Correct? Now, look at A1, A0. A0 is on the perpendicular bisector. A1 is over here. This angle is going to be equal to phi 12/2. And let us consider B1, B0. Again, it is half of the angle, so it is also equal to phi 12/2. Consider A1, B1. It is equal to alpha. It subtends alpha at P12. And P12 M is alpha. So is A0 P12 B0 is equal to the angle alpha, because A0 and B0 are on the perpendicular bisectors. Now I have a conclusion. Cranks A0A and B0B subtend the same angle at the pole, or angles differing by pi. I'll explain why that is true. In this case, it is, in this figure, it is, they subtend the same angle alpha. This angle is equal to the halves of the angle of the rigid body, angular rotation of the rigid body at the pole. Phi 12 is the property of motion. It is the same for any point A and A0. If you select, it doesn't matter where A, B is selected. This is true. If that is the correct A0, you know, you can have any point A and A0. Two, the coupler and the fixed link, A1, B1, AB, and A0, B0, subtend equal angles at the pole, all angles different by pi. This angle is alpha, or alpha plus pi. Let me repeat, I'll show why it is alpha plus pi in a minute. Alpha is not the property of motion. Whenever you select a different point A1, whenever you select different point B1, alpha is going to change. Whereas phi 12 will not change as long as it is the same motion. P12, phi 12 are the invariants. They do not change by your selection. Between two positions in complete, P12 and phi 12 completes, defines the two positions. One other important thing, any point on the moving body is going to have two locations, in position 1, in position 2. But there will be one point, there is one unique point on the moving body which will have the same location at the two positions. position 1, position 2. And that is P12. Only P12 is at the same location for position 1 and 2. Any other point on the moving body is going to have two different position points, A1, A2, C1, C2, D1, D2, etc. But P12, P12, will be P12, okay? That's why we only say P12. It is common for position 1 and 2. That's the pole. That's the property of the pole. That's very important. Is that agree? Okay. I think I'm not going to analytical methods today. I will cut my lecture for today. I'm sorry, I have an important thing to attend. I will stop sharing. I will try to answer any questions you may have. I will try to answer your questions. Are there any questions, please? I know I'm going to stop, so I'm not going to give a break. I will end the session lecture right now. But first of all, do you have any one of you have any questions, please? It is very simple, but the concept is very, very important. Everything that I have stated, every word I have stated, I will be using it throughout the course. Fixed pivots, moving pivots, center point, circle point, homologous points, all those concepts we will be using for the rest of the course. Okay? I think I'll stop now. Next week, I'll discuss the analytical methods and so on. You are given homeworks. Please do those homeworks using geometrical method only. I have shown geometrical methods. Please read whatever we have posted. Chapter 2 you have in your hand. They will be covering it next week as well. And maybe for 3 weeks, we will be discussing chapter 2, because these are very important concepts that you have to learn, because we are in 2 positions. We are going to have 3, 4, and 5. So whatever I have stated right now in this lecture, I will be using it for almost all throughout the course. Any questions you may have, I'll try to answer. Any questions, please? So shall I expect that all of you have understood what I have said? Okay, I'll stop. Have a nice time. See you next week.
İyi günler hocam.
İyi günler.
İyi günler hocam.
İyi günler hocam.
Çocuklar lütfen soru sorun. Bakın yani soru sormazsanız ben çok hızlı giderim. Onu söylüyorum. Yani soru sorun. Lütfen çalışın, soru sorun. Okuyun. Yani okuyarak öğrenmeniz de önemli, çok önemli. Hele bu devirde eğitiminiz, öğrenmeniz, defteri kapatmıyorsunuz mezun olurken ya da bitirirken. Devamlı olarak öğrenmek durumundasınız. Benim şu anda eğer mezun olduğum zamanki durumda kalsaydım şu anda size anlatacağım bir şey yoktu. Fazla bir şey yoktu. Devamlı olarak öğrenmek durumundayım. Geogebra'yı ben 70 yaşından sonra öğrendim. mutlaka öğrenmek mecburiyetindesiniz. Çünkü teknoloji değişiyor. Newton kanunu duruyor ortada. Newton kanunu kullanıyoruz devamlı olarak. Fakat uygulamalarımız, bakın Newton kanunu ilk önce trenler için buharlı, bütün makine mühendisliği buharlı lokomotiflerden gelişti. Fakat şu anda buharlı lokomotifle uğraşmıyoruz. Ondan sonra içten yanmalı motorlar üzerinde çalışıldı. Ondan sonra şimdi ise daha farklı konular var önümüzde. Devamlı olarak konular değişiyor. Ama temel değişmiyor. Ama devamlı olarak da yeni konular çıktıkça sizin yeni şeyler öğrenmek mecburiyetiniz var. Eskiden kalırsanız yani mesleğinizi yapamazsınız. O kadar hızlı bir değişim var ki dünyada, devamlı olarak onu takip etmeniz lazım. Devamlı olarak öğrenmeniz lazım. Ve öğrenmek için de yani gidip de birisi size anlatmayacak. Sizin gidip okuyup öğrenmeniz gerekiyor. Sizin gidip bir şeyleri araştırmanız gerekiyor. İnternete bakmanız gerekiyor. Patentlere bakmanız gerekiyor. Öğrenmeye aç olmanız lazım. Öğrenmek istemeniz lazım. Öğrenmek istemiyorsanız, yani aç değilseniz benim sizi tutup ağzınızdan bir şey sokacak halim yok. Kimsenin yok. Siz öğrenmek istiyorsanız öğrenin arkadaşlar. Ben elimden gelen yardımı yaparım. O kadar. Öyle düşünün. Yani mutlaka siz kendiniz sahip çıkın eğitiminize. Bu devir bu şekilde. Ve samimi söylüyorum, bana sorarsanız hayat benim gençliğime göre sizin daha zor. Siz daha zor bir ortamda yaşayacaksınız. O zaman kendinizi daha fazla yetiştirmeniz lazım. You have to make the difference. Peki, iyi günler, görüşmek üzere.